session, right. So, in the previous session we discussed about the basics of frequency domain analysis. We had seen the concept of gain margin, phase margin, omega GC, that is gain crossover frequency, and omega PC, phase crossover frequency, right. In today session we will discuss about the polar plot, right. So, polar plot is one of the frequency domain analysis, where we would like to check the stability of closed loop system with variation or with respect to the frequency, right. So, here in today's session we will discuss about the polar plot, and then we will see the basic steps that is involved in design of polar plot. So, in the last session that we discussed that if you have to find the value of omega GC, that is the value of gain crossover frequency, we need to put our mod of GJ omega equal to 1, and we had also seen to determine the value of omega PC, we have to put our angle that is equal to minus 180. So, when we use these two condition, then we can determine the value of omega GC, that is gain crossover frequency, and value of omega PC, that is phase crossover frequency, which will help us in determination of gain margin and phase margin. So, we will see in this lecture how with the help of polar plot we will calculate omega GC, omega PC, and then we will calculate the gain margin and phase margin, and we will determine the stability of closed loop system. So, now we will see here the definition of polar plot, right. So, if we consider any sinusoidal transfer function g j omega, right, it means we would have given GS, okay. Suppose GS given is 1 over s plus 2, right. So, if I have to write the sinusoidal transfer function, what it means, I need to replace s by j omega, right. So, I discussed this concept in the previous lecture. Whenever we replace s by j omega, then it will become a sinusoidal response, right, or you can say it will become a sinusoidal transfer function. It means our input is sinusoidal signal, okay. And then we need to calculate mod of this g j omega and angle of this g j omega, and then we need to plot it on the polar coordinate, where we need to vary omega from 0 to infinity, okay. So, this thing we need to do in the polar plot, right. So, we would have given this GS, that is a open loop transfer function, right, and then we need to calculate g of j omega by replacing s by j omega, then calculate the magnitude, calculate the angle, and vary it from 0 to infinity. Then we will determine the stability of closed loop system. It means again we are doing same thing, we are observing the open loop system and keep varying response with respect to frequency and observing the stability of closed loop system, okay. So, this plot will consist of, you can say, mod value of g j omega and angle of g j omega as function of omega, okay. And this will give us the locus of all point, you can say mod and angle as omega varied from 0 to infinity, okay. And this generally you can say the angle is measured with respect to, you can say, positive j omega axis. If it is positive, then we can say we are moving in anti-clockwise direction. If it is negative, it means we can say it is in clockwise direction. So, this direction of angle we will see in next slide in detail. It means how to determine whether we are moving in anti-clockwise, whether we are moving in clockwise direction, okay. Then polar plot is very useful in determination of stability of closed loop system from its open loop response or open loop frequency response. So, as I told you, we have to observe open loop system and we have to vary its magnitude and phase with respect to frequency from 0 to infinity, and then we can estimate the stability of closed loop system, right. So, basically what we are doing in polar plot, we are mapping the S plane into GS HS plane. So, here a concept of mapping will come in the picture that will help us in the concept of Nyquist plot, right. So, whatever our open loop transfer function GS would be given here, and then we need to convert it into the GS HS plane, right. So, here in the S plane I am plotting the real value in the x axis and imaginary value in the y axis. right. When we have done this mapping, then in the x axis real part of GSHS I need to plot, and imaginary part of GSHS I need to plot on the y axis. Okay. So, this will be the mapping that will happens in the polar plot, right. So, here we need to plot this phase, and sorry, this is the phase and this is the magnitude with respect to frequency, where frequency is varying from 0 to infinity. Okay. So, this is what mapping from S plane to GSHS plane, right. So, during this polar plot, we need to observe here our old characteristic equation, which is giving us the closed loop pole, right. So, 1 plus GSHS that we have to use, right. So, what is GSHS? Sorry, what is this equation? We already discussed in previous unit and previous lecture also. So, here to determine the critical point in the polar plot, I have to equate this equation equal to 0, and GSHS will equal to minus 1 plus J 0. So, minus 1 plus J 0 will be a critical point in the polar plot, right. So, how this critical point will help us in determination of stability, we will see in the next session, right. So, we will observe that determination of phase margin, gain crossover frequency, and phase crossover frequency is moving around this critical point, that is minus 1. Okay. So, we will discuss about this concept in next session, right. So, now we would like to see what would be here clockwise movement and anti-clockwise phase in the S plane. So, whenever I am moving in anti-clockwise, so I will write here ACW. In some textbook you will find it as CCW, that is counterclockwise. Okay. So, this is my 0 degree, and I will move in the anti-clockwise direction by angle of 90, and I will get here plus 90, and again I will move further anti-clockwise, then I will reach to the plus 180. Further I will move by angle of 90 degree, I will reach to plus 270. Further I will move by 90 degree, then I will reach to 360, or you can say 0 degree again. So, this anti-clockwise movement will give us positive phase, right. So, you can observe whenever I am moving, so I am getting here positive sign everywhere. So, this is the anti-clockwise movement in S plane. What about clockwise? Suppose I am standing here at 0 degree, if I am moving clockwise, then I am getting here a phase shift of minus 90, right. My direction is clockwise. Again, if I move clockwise by 90 degree, I will reach minus 180. Again, if I move by minus 90, I will reach to the minus 270. Again, I will move by minus 90. So, I will get here, you can say at this point I reaches to the minus 360, or it is equivalent to 0. So, this movement is clockwise movement in the S plane. Okay. So, always remember, whenever we are moving in clockwise, we will get always negative phase. When we move in anti-clockwise or counterclockwise, we will always get positive phase. Okay. This concept we have to follow in polar plot, right. So, now we would like to see the basic steps involved in design of the polar plot. So, first we would like to see for type 0 system. So, for type 0 system, I am taking here a open loop transfer function G s equal to 1 over S plus 1, right, and we need to draw polar plot for this, right. So, an open loop transfer function is given to us, and then we need to draw here polar plot to determine the stability of closed loop system. It means, when I place this open loop system in the feedback, then what are the basic factor which will make it stable. Okay. So, this can be determined using the polar plot. Okay. So, step 1 is we have to obtain the sinusoidal transfer function, right. So, we need to replace S by j omega. Okay. So, S by j omega, then this is my transfer function in terms of j omega, that is g j omega equal to 1 over j omega plus 1, right. Now, step 2, we need to calculate its magnitude and phase. Okay. So, whenever I am determining here mod of g j omega, so it would be given by 1 over under root of omega square plus 1. Okay. So, this concept you had seen in the complex number. So, this you can recall it to determination of its mod and phase, and if I want to calculate its phase, then I can write here it is phase in the numerator is 0, denominator is tan inverse of omega, and if I make this or move this denominator phase in numerator, this will become minus of tan inverse omega, right. So, this is the determination of magnitude and phase of open loop transfer function by putting s equal to j omega. So, this is a normal simple step. Now, step 3 we have to vary omega for magnitude and phase from 0 to infinity. So, for that purpose we have to make a table, right. So, in the table I am keeping omega here. First I am making omega equal to 0, then I am making omega equal to infinity. So, in that case I need to see what is my mod value. Okay. So, here you can see when I put here omega equal to 0. So, this would be value 1, you can put omega equal to 0, right, this would be value 1. It means when my omega is equal to 0, this value is 1. So, what will be the magnitude when omega is going to infinity? So, you can see when I put here omega equal to infinity, then whole response will become 1 over infinity and this will be equal to 0. It means at omega equal to infinity my magnitude is 0. In the same way I need to calculate my phase for omega equal to 0. So, I had done this calculation, my angle phase given by minus of tan inverse omega. It means my phase is here function of frequency. So, first I would like to put omega equal to 0, then I will get here tan inverse 0, that is 0. Okay. It means when my omega is 0, my phase is 0. Okay. And then okay, if I put here omega equal to infinity, so I will get here minus 90, right. So, omega infinity you can say tan inverse infinity, tan inverse infinity is equivalent to 90 degree, minus sign is here, that is why we will get here minus 90. Okay. So, here at omega equal to infinity my phase is minus 90 degree. Now, see what is happening, whenever my omega is 0, I was standing at 0 degree if we observe with respect to phase, and we are moving towards minus 90. It means we have to move here in clockwise direction. Okay. So, we will move here in clockwise direction 0 to minus 90. Okay. So, here what is happening, whenever I am starting my magnitude is 1 at omega equal to 0, my magnitude is here 1. Okay. And I am moving, and if I have to move, then my omega you can say is going to infinity. So, I am moving where I have to move? I have to move towards the minus 90. So, minus 90 is here and I have to move in down direction. So, whenever I am moving towards minus 90, so what is happening at omega equal to infinity? My magnitude is going to 0. Okay. Where is 0? 0 is at the origin. It means whenever I am approaching towards minus 90, my magnitude is moving towards the 0, right, and this will be my polar plot for this function, and here my real value is real of GSHS and my this y axis is imaginary of GSHS, right. So, this is the mapping of you can say S plane to GSHS plane, and this is the polar plot, right. So, here this graph exactly should start from 1 and it should terminate at 0. So, you can say for type 0, you can say here my omega is 0 and here my omega is infinity. This is my start point and this is my end point. Okay. This thing we have to remember, right, and we can say this is my type 0 system, it is starting in this quadrant and terminating here. Okay. So, here if I say what is the order would be 1. Okay. So, here if we see the transfer function, so this is type 0 and order 1 system. Okay. Now, we would like to see basic type and order. So, when we discuss about type 0 system, it means when no pole lie at the origin, my polar plot always start from here, and if it is order 1, it will terminate towards minus 90. Okay. So, here order 1 will terminate at minus 90, right. In the same way, if we go for type 0, and you can say we will come to that graph. So, for type 0 and order 1, what we had seen, our transfer function, generalized transfer function would be k over 1 plus st1, and our polar plot would be like this. Okay. This value you can say that may be k. This is my omega equal to 0, this is my omega equal to infinity, right, and this is my start point and this is my end point. So, now what will happen if I am going for type 0, but order 2, right. So, in this case you have to look for the phase system. Okay. So, if I calculate phase for it, that is for this transfer function, my phase angle of or phase of g j omega would be given by minus of tan inverse, you can say, if I assume omega t 1, okay, and this would be, you can say, minus of tan inverse omega t 2. Again this phase is function of this 2 omega, right. When my omega reaches to infinity, sorry, whenever my omega is 0, then this phase is 0. When my omega is infinity, then this phase would be minus 90, minus 90 would be minus 180, right. It means for type 0, my polar plot will start from 0 degree and it is terminating at minus 180, right. So, I can say it will go and terminate like this. It means this polar plot is going here in clockwise direction and it is entering at the angle of minus 180 and it will terminate here. So, here my omega would be 0 and here my omega would be infinity. Okay, right. So, what we get this information, if I am going for order 2, then this would be my termination of polar plot. Okay. In the same way, when we go for type 0 order 3, we will get here 3 phase and our termination would be minus 270. Okay. So, what would be polar plot? I am doing this directly, you can do the manual calculation. So, I will start from 0 degree and I have to terminate at minus 270, right. I will move like this and then I will terminate at minus 270. Okay. So, what is happening? This is my omega equal to 0 and here my omega is infinity. Okay. It means my polar plot will terminate at the angle of, you can say, the phase of or toward the phase of minus 270. So, we can make here a generalized concept, whenever my system is type 0 and order 3, it will terminate across minus 270. Okay. This is 0, this is minus 90, this is minus 180 and it will terminate across minus 270. Okay. In the same way, for type 0 order 4, the 4 phase would be here. Now my phase will change, final phase will change to minus 360. Okay. It means what would be our polar plot? Our polar plot start from 0 degree and it will terminate at minus 360. Here omega is equal to 0 and at origin you can say my omega would be infinity. So, this is termination of order 4. So, we can say here my order 4 of type 0 system will terminate along the direction of, we can say, minus 360 or 0 degree, right. This is for type 0 system. In the same way, when we go for type 1 system, so for type 1 system and order 1, we would like to see k over s. Same format, I have to replace k by j omega, sorry, s by j omega. I will get k over j omega. I need to calculate its mod of g j omega, that will gives me k over omega. I need to calculate its phase. So, phase in numerator is 0 or minus tan inverse of, or sorry, not tan inverse of that, because I will get here minus tan inverse of omega. Real part is 0, omega by 0, and this will gives me minus tan inverse infinity, and it is minus 90. So, phase is coming here minus 90, and it is not depending on omega. So, when my omega equal to 0, phase will remain same. When my omega is finite, phase will remain same. Okay. When my omega, you can say infinite value, then again my phase would be minus 90, because it is not function of omega anymore. So, whatever value of omega I will put, I will always get my phase minus 90. Okay. So, what would be polar plot for this? Okay. So, I need to make that table. You can say when my omega is 0 and omega is infinity, I have to look for mod of g j omega and phase of g j omega. Okay. So, initially when I put omega equal to 0, my mod would be infinity. When my omega is infinite, this value would be 0. Okay. First step. Second, my phase, whenever my omega is 0, it is minus 90, as I told you. Whenever my omega is infinity, again it is minus 90, right. It means my polar plot will initiate to from the phase of minus 90, and it will terminate to the phase of minus 90. Okay. So, here you can see this is my 0 and minus 90, right, and this will be my polar plot, right. It means my omega equal to 0 is here. You can say the mod is infinity. So, I will start from the infinity, okay, and I am terminating to the origin again at the phase of minus 90. So, that is why I will start from minus 90, terminate at minus 90, and here I can say my omega value is infinity. So, this is the polar plot for type 1 order 1, right. In the same way, when we go for type 1 order 2, then we will get transfer function like this, and when we calculate phase, you can say mod of, sorry, angle of g j omega at omega equal to infinity. This will gives me my angle of termination minus 180. Okay. So, what would be polar plot for this function? I have to start from minus 90, you can calculate, and I will terminate at minus 180. So, I will get a plot like this. So, we can make this one statement that whenever my system is type 1, it will start from phase of minus 90, and whenever it is order 1, it will terminate across minus 90. Whenever it is order 2, it will terminate across minus 180 for type 1. In the same way, whenever it is order 3, then it will terminate across minus 270, right. So, this, sorry, minus 270 would be here. In the same way, for order 4, it would be across this direction. So, this is our generalized concept that we can use to draw the polar plot, right. So, directly I would like to complete the remaining plot. For order 3, my polar plot would be like this, start from minus 90, and it will terminate across minus 270. In the same way, when I go for order 4, I will start from minus 90, and then I will terminate across minus 360 or 0 degree. Okay. This is the polar plot for type 1. In the same way, polar plot for type 2. So, here my type 2 order 2 is here, it is k over s square. It means k over, I have to replace this s by j omega, k over j omega square, right. So, if single pole lying at the origin, total phase is 90. If two poles lying at the origin, total phase is minus 180. Okay. It means I will get here minus 180 degree phase shift, right. So, where my polar plot will start? So, you will find in this case again my phase is not function of omega. When I put omega equal to 0, I will get minus 180. When I put omega equal to infinity, again I will get minus 180. Okay. Initially my magnitude would be infinite, and when my omega moves to infinity, this will become 0. Then my initial plot start from minus 180 with magnitude of infinity, and as I move omega equal to infinity, it will terminate to 0. So, this is omega equal to 0, this is omega equal to infinity. Here my mod of g j omega is infinite, here my mod of g j omega is 0, right. In the same way, for type 2 order 3, my polar plot start from minus 180 and terminate at 270, minus 270. In the same way, for type 2 order 4, my polar plot start from minus 180 and terminate at minus 360. Okay. You can calculate all those value and you will found polar plot like this. Okay. So, this is the generalized polar plot. In the same way, when you go for type 3 order 3, then your polar plot start from minus 270, this will be polar plot, and when you go for type 3 order 4, then polar plot start from minus 270 and it will terminate at minus 360, right. So, directly we are doing this without any calculation, right. So, this is the basically a polar plot whenever there is no 0 present in the transfer function and no pole lying in the right half plane. So, directly observing the transfer function, we can draw the polar plot. So, remaining concept we will discuss in next session. Thank you for today.